Hi everyone, and today we are starting with the Lagrangian formalism, and this basics somewhat. I go through these some essential things, and we'll get into some problems only, right? So it is the Lagrangian. So it's a kind of a formalism. Newton's equations are the most fundamental equations. It works everywhere. In all the formalisms, Newton's equations play an important role. Okay, that makes that gives the sense for the mechanics, right? So in Lagrangian formalism, and L, which is given as Lagrangian, is a function of q dot and t, and q is the generalized coordinate here, right? And q dot is the generalized velocity, right? And t is the time. And initially, we discussed the problem without t. That is, t is explicit. We can't find t term explicitly, right? So the Lagrangian L is given as t minus v, and t is the kinetic energy, and v is the potential energy. And this is the Euler Lagrange equation, which is d by dt of dou L by dou q dot minus dou L by dou q equal to 0. And particularly, this is for the conservative systems, right? So for conservative systems, you don't have external force, so we have 0 here. Once you have the non-conservative system, then you have an additional term here, right? So once you know the kinetic energy and potential energy of the system, without you don't even though you don't have an initial condition for the system, you are able to write the equations of motion with the help of a Euler Lagrange equation. So that's what the idea is. So now let's get into the some basic or a easy example which uses Lagrangian formalism to solve. Here I will be using a area harmonic oscillator problem in one dimension, right? So the Lagrangian L is equal to T minus V. T is the kinetic energy. In general, we write it as half mv square. So instead of V, I will be writing x dot, right? So instead of V, I will be writing x dot, and of kx square, which is the potential energy for a spring mass system. Once you have a spring mass system, the potential energy which we have is of kx square. And here we have a generalized coordinate x and generalized velocity x dot only. Okay, you can see that there is no explicit t in this given Lagrangian, right? For the linear modulus particular. So the other Lagrangian equation, which is d by dt of dou L by dou q dot minus dou L by dou q equal to 0. So this is the other Lagrange's equation. And here we have, as I said earlier, I have only x dot here, right? I have only x dot here. So I can rewrite that Euler Lagrange's equation only using x dot, right? Then I have to find this term, right? So I have to find d by dt of dou L by dou x dot. I have to find this term, and I have to find this term, right? So with the help of L, I can do that. So dou L by dou x dot equal to of, then I have to differentiate mx dot square, then you will be getting 2mx dot, so I can write it as mx dot. So and then I have to differentiate that with respect to dt, and there's a m which is the constant. So note m is this, it's a non-relativistic problem, so m is the constant, and once you differentiate with respect to t, and it will become mx double dot. Then we have to analyze this term, where we can get this term with the help of L dou L by dou x, and term is only present in a potential energy. So there's a negative sign here. There's a negative sign here. So once you differentiate that with respect to x, you'll be getting 2 by 2 kx. Then there's a negative sign, and once we have that, we are able to write dou L by dou x equal to minus kx, right? Dou L by dou x equal to minus kx. Once you get this, we know d by dt of dou L by x equal to mx dot. So I wrote that mx dot here. Then dou L by dou x, which is minus kx, and here we have a minus sign here. So mx double dot plus kx equal to 0. Then we have x double dot. I am bringing that m as a denominator for this term, so it will become x double dot plus k by m, x is equal to 0, right? So this is with the help of this equation you are able to study the dynamics of the system, right? So that's how the uh, Lagrangian formulas number. Once you have the kinetic energy and potential energy, you are able to write the equations of motion. Okay, we will stop here. Then we will discuss some more example in upcoming videos. Right? We are going to discuss very simple examples. Thank you.